Now, but this entire process uses so many data structures, and that's what I really wanted to bring it to you to understand that sometimes, because the students are considering that data structures, or why we are being taught the data structures and all those aspects, but data structures are the most important uh, subject actually for any computer engineering task actually. So, if you just recall, we have discussed about the different phases and the different processes the compiler carries out. So, say lexical analysis. Now, lexical analysis uses queue, linked list for token streaming. So, there are multiple, these are again different data structures. During syntax analysis, it requires an n-ary tree. You people have been thinking binary trees only, where a maximum of two children are permitted, but in n-ary tree, n children are permitted, and these are more complex trees. So for parsing, such type of trees are required to be constructed. Then we have the semantic analysis, where we check whether the expression is a valid expression or it's not a valid expression. So we have the hash tables for symbol tables. Then we have the intermediate optimization. So here we require directed graphs to check whether the control flow is proper or it's not proper. Then for code generation, it uses the interference graphs. So graphs are required here. So many data structures, and the most important data structure is symbol table, which is used across all phases, and it is usually implemented as a hash table because it is used quite frequently. So we need to ensure that the program efficiency is not lowered by using an inappropriate data structure for hash table for the symbol table. So we use hash table for a constant time, which we call as the order of one lookup. Then we can have a scope stack. I'll just tell you what is a scope of a scope stack. So there are so many data structures, and I think that might have given you an idea that why we always insist upon learning the data structures very efficiently, and in-depth knowledge of data structures is must for any computer engineering, whether it is programming or any other subject you are dealing with. So importance of data structures is unlimited actually, and those who are good at data structures and more efficient in data structures, they have a lot of opportunities for themselves in the job market. Now, once the loader has loaded the address of the first instruction in the program counter, the next process begins. So this is what we call as the runtime phase. So once the control has shifted to CPU, it enters the infinite hardware loop. Why I'm calling it an infinite? Because really CPU doesn't know whether your program has such instructions or such situation may appear where the program execution keeps on happening and happening and happening. A set of instructions is getting executed again and again, because that may be a runtime situation and may not be a compile time situation. Remember, compile time situation will be identified by during the compilation phase, and it will be highlighted either as an error or a warning. So if that is the case, absolutely not to worry about, but you need to be worried about infinite execution during the runtime, and that is where one thing you need to be very sure about. Okay, so now here there are lot many stages actually. See, why these, so what CPU does actually, there is a what we call as there are multiple stages of the instruction execution. Now we are not talking of the program execution, but we are talking of the instruction execution. So the first is in fetch. What is fetch actually? See, your actual instruction is stored in somewhere in the memory location, which the loader has been assigned by the operating system. Now, this instruction needs to be passed on to the CPU. So, in CPU, we have what we call as the instruction registers. So, the first task the CPU does is it fetches the instruction. So, the instruction pointer grabs a byte instruction from the text segment in the RAM, and it loads first it decodes. So what is the internal circuitry required for that binary instruction? So that is called the decoding. So internal circuitry breakup, the binary layout co-op, because let me just give you an example. See, uh, the instruction may be something like this: add 6 comma 5. I've just taken a very simple example, that add is the instruction, add is the instruction, and 6 and 5 are your operands, we call them. So here I have taken constants, and the intent is that we need to add 6 and 5. So what during decode will does that, during with add actually, it will generate the corresponding, because binary code is already available. So this binary code basically refers to something like a key on the piano. So if you see the CPU is something like this. So this is your CPU. Now what the CPU is actually, CPU can think it's not a single hardware circuit. Actually, it is comprising of multiple hardware circuits. So suppose this is your adder. This is your adder. Okay. Now what the adder does, it's a circuit actually which adds two numbers. Okay. So you need to, for this particular operation, what you require is, you require to instruct the CPU that, okay, this is the circuit which we need to invoke for this instruction to be executed. So what that instruction does is, actually it is something like a piano button. So what we'll do actually, we'll press that button to generate a specific sound actually. So that is the instruction, meaning of the instruction. And then you have these operands. These operands will be applied to this adder. There are some other ways involved also. For the simplicity purpose, I'm just saying. So you can think of the adder something like this, that this is your adder. You have two inputs here. One is 6 and this is your 5. And this is your 11 is the output. So that's how. So this 6, maybe if it is a constant, then it is in one memory area. If it is variable, then it is another memory area. So all these operations required to be performed during with the registers. So that's what it happens. So distinguishing the internal registers, what it means here when we are saying register. So what we does is, if it is an addition, then instruction is required to be executed accordingly. So that way, the that is called the decoding actually. Then what it does actually, it executes the instruction. Now this I have already so arithmetic and logical unit will apply these data operands to the circuitry, and circuitry will give you the output. So structural transistors, the particular gates or the transistors are fired up, and they use it for computation of the results. Okay. And then what it does is, now the result, you have obtained the result. So this needs to be sent back to the memory location. So that is called the write back. So the final step of execution is saving the output. So the calculation is written into the memory. So again, so before writing it into the memory, it is written first into the internal registers of the CPU, and then the internal registers will transfer it to the memory address, the RAM actually. So this is how the entire execution cycle, if you see, it comprises of four sub processes: fetch, decode, execute, and store. Okay. And then what it does, because now this instruction has been completed, so we need to add the load the program counter with the next instruction. So it loads the next instruction into the address of the next instruction into the program counter. And with this actually, now execution of one instruction is complete. So you can understand, it's not a one step process that, okay, you press a button and you get done. You may be feeling that way, but internally there are many processes involved. Okay, now here is an example of an execution cycle. So step one, if you see here, if you see it here, so the instruction is stored here. So the program counter, that's the first instruction. So in the step 1, the program counter will get now. So once what the loader does actually, if you see it here, the program counter is loaded with 3A24, where is the first instruction is loaded. First instruction exists in the memory, so the program counter is loaded with this address. Now in the step 2, which once the program execution starts, what it does is it fetches the instruction. So in within CPU, what we have is we have the instruction registers here. So the instruction code is loaded within the instruction register. Now in step 3, because the instruction will require the operands also, so the operands are loaded in the data register. So that is your step 3. So operands are say at 3A25 and 3A26 addresses, so they will be loaded into the operand registers. And so this is your step 4. And then now the instruction processing logic has got all the things, because with the instruction code, the hardware has been invoked, it has got the operands. So now it will process, and so the data will be fetched here. And then in the step 7, we have the results which are available in the data register, and then finally this will be written back to the memory, where the results will be written back to the memory. So this is called one complete execution cycle. Okay, and so you can see there are a lot many processes involved here. Okay, now the question is, what is the role of the stack? Because what really when we are talking, why we are talking of the stack and all those things, what are the different data structures involved in the program execution? So what happened was, in the beginning when the programming started, it was a static memory allocation. So all the variables, if you see here, these addresses 58F1 means these data will be in static addresses, so you don't require any kind of stack there. But now with the development and with the more sophisticated programming required, this kind of static arrangement doesn't work. So what we require basically is we require to use proper data structures and proper structs for ensuring that dynamic situations can also be handled. What those dynamic situations are, we'll see. So this worked quite fine until we wanted to do two things. We were not doing anything like nested function calls and the recursion. So till then it was not required, but now recursion is becoming a default programming style, and it's a very efficient programming style. So for that to be really using and making possible to use, we require a stack. What that does, that will be clear. So without a dynamic stack, this a modern program would instantly overwrite its own data and crash, and that is where the role of the stack comes. Okay, so let's just understand what is a stack actually. So before stack actually, why we use the stack actually. So during program execution, the stack, which we call as the call stack, it's a dedicated region in the memory which manages your function calls, your local variables, and execution context. Execution context means when you have the local variables and global variables, both, which particular variables to use depending upon the context, that is decided by the stack. And for that to enable, we require a stack. So these are some some of the functions the stack perform. So the most important is function call depth. So what without a stack actually, you cannot have a function calling function quite deep. Means one function calling one another function, the second function calling the third function calling the fourth function, and so on and so on. That is not possible if we have a static memory only and we don't use the stack. But with the stack, that is virtually unlimited. There it's actually it's not unlimited, but only virtually it is unlimited. We'll see what is the meaning of that actually. Then recursion, because recursion what happens is one function calls itself. So let me just take an example here. Now suppose I use fx is equal to fx minus 1 plus 2. I am taking a very simple case. Okay. It means to compute the value of fx, I require the previous value. That is called, this is a recursive call. So basically, what will happen is, suppose I have a code written for fx here, then the same code is applicable for fx1 also. So this is called a recursion. So fx1, how fx1 will be defined now? Fx1 would be fx minus 2 plus 2. So now we require fx minus 2. This is called recursion. Now, without a stack, using this kind of programming style is impossible. And in good number of cases, it's very difficult to write a program without using recursion. So stack is very, very important for that aspect. Similarly, we require for memory cleanup, because some of the, particularly when local variables we are not, they are no longer required. In a static memory case, we'll require to delete those variables, otherwise they'll keep on occupying the memory. Manually, we have to delete them, and for that we'll require to write the code in our program. But with the stack, that is not required, no longer required. Stack handles it automatically. And then the speed, it makes the program execution quite fast. So let's understand what is the meaning of the stack frame, because what happens is, remember, the purpose of stack is to ensure that the data related to one function is not overwritten by the data of the other function. So what you can think of it this way, that okay, suppose I have a function fx here and I have a function fy here. So the requirement is that this data should not overwrite here. And once this, suppose fx has completed its execution, then this needs to be preserved. So we need to come back to this aspect. So for that, actually, what it does, the stack frame basically refers to this particular portion during in the stack. Remember, this is whole is called the stack, and this is called a stack frame. So basically, the function arguments, the inputs passed on to the function, then it has the return address, the saved frame pointers, because this particular frame starts from this particular location here. If you see it here, it starts from here. So that way we need to save this address also, and then the local variables are also required to be. So this is called sometimes an activation record or a stack frame, but this is an important part of the stack itself. Now, how the stack does? Just try to understand this aspect here. So here I have taken a very simple code actually. So suppose you have, this is your function which you have written, okay, and this is the main where you will be using this function square. Okay, now see here, the call is here. Remember, the program execution will start from this. So what it does actually, the first is because program counter is loaded with this address. So inside main, if you see the line 5 and 6, this is how the main stack frame is created first. So because this is a function, so this frame is created and it looks for the local variables, and it really doesn't know how many variables are there. So it will keep on pushing them onto the stack. Okay. So that is the first step. So when the program boots up, the operating system executes the main. The CPU creates a stack frame for main to hold its local variables. Okay. Now step B, just see, now at line 7, what we have is, we have this line. Okay. So this is a variable within main, int final result. So this is a variable which is created within the main. Okay. So here what will happen is, so if you see the main stack frame, it contains the length is 4, and what is the value it doesn't know, because it has still not been computed. So a final result, this is the variable which has been created. Now then next line, if you see, it has a call here to the function square. Okay, whereas square is written here, so it has a different address. Now if you just recall, the requirement is that once this code is executed as this function call, we need to return here. That is this particular line. I'll, for your simplicity, though it's not an executable line, but just for the simplicity, I'm pointing out here that okay, it needs to. So after this instruction needs to be executed. So how this address will be loaded into the program counter, that is where the role of the stack pointer comes actually. So what it does, see the square, the parameter is side. Just see it here. The parameter, this is the parameter here. So this is the side is the parameter. Then it requires a return address. So back to main. So this return address here, this return address, this will be pushed onto the stack. And then it has a local variable. See, it has a local variable area. Okay. So this local variable will also be created within the stack. So you have the local variable area, and because we are passing it with 4, actually the value with 4, so the value is 16 here. So this value is also written here. So once inside square, it allocates a space for its own local area. So this is another stack frame. If you see, this is one frame and this is your another frame. Okay. Now here one more word is shown here, stack pointer. Stack pointer always points to the top of the stack. Okay. So when this particular code is getting executed, it knows that okay, this is the top of the stack. So stack pointer will point to it. Now this is the stack pointer which keeps on moving with the execution and the completion of the function call. So once this function call is completed, what it does is it, because remember, this entire frame needs to be destroyed. Once it is destroyed, what it requires the address where it will go back. So here this stack frame where it has called, so here this will return here. So the stack pointer, once this is deleted, so the stack pointer will move here automatically, knowing which address it needs to return to. That is the stack in action. Okay. So once that happens, just see it here. The stack pointer is now pointing to the final result, which is 16, and that's how. So this is returning from the square lines 3 and 4. So when the CPU hits the return area, it grabs the calculated value and looks at the saved return address and jumps back to the main. And instantly the CPU adjusts the stack pointer backwards. The square stack frame is popped up. What we have already discussed, that it will be popped up, that is, it will be deleted and effectively destroyed, and return value is written onto the final result. The stack will do. See, if you have been using a static memory allocation, then you would have required to delete this portion, this memory manually. So you would have required to write the code for deletion of this memory also. But with stack, actually what is happening is once this execution has completed, it is automatically deleting it, and so you don't require it. So it is automatic cleanup is offered by the stack. So we never had to write the code to delete the area variable. And so the moment square is finished, its memory space is reclaimed automatically just by shifting the stack pointer. And the stack always does is leaf order. And that's why if you just remember that function calls are always nested. So, and we cannot have a function call this way, that suppose this is your, this is your, I'm writing here, F1. So this is your F2, the function calls need to be this way. It cannot be that, okay, your, suppose this is your F1, then you cannot have your F2 this way, because then this is not nested actually. This is a violation. What is kind of violation? That is basically, because what will happen is, just see, F1 cannot finish its execution till F2 is finished, and F2 cannot finish because till F1 cannot finish. So this is an this is a situation where the program execution will never be completed. So for that to happen, the function shall also always be written in this order. That is, The scope of one function can be within the another function, but it should never cross the boundaries of each other. So if you see, this is the summarization of the entire stack in the runtime memory. So initial process we start. So we have the stack and heap. The purpose of heap will also be discussed. So we have the data, and so we have the stack, the data. Then we require to adjust the stack, and then this is the entire stack. And these are some other system frames. These are some other kind of data which is written here. So first function call, it will have the arguments, the return addresses, the saved base pointers, and the local variables. All this is called one stack frame. This becomes one stack frame. Okay. And this frame pointer will point to the first where the address of the stack frame begins from. Okay. And then all these, once it is completed, so if we have the nested function calls, so see what happens. This is the one, so this is LIFO, so the function 2 frame is added above function 1. So this is your function 1 here, see, and then it will be added over the function 2. So once, unless the function 2 execution is completed, function 1 details will not be revealed. And that's how it happens. So once function 2 returns, this entire space will be deleted and the contents transferred to the main memory, and then it will resume the execution starting from function 1. So that's how the full call and return is shown here. So you have the main, you have the function 1, then you have the function 2, and then return to press the process exit. And that's how, so that's the very, very important role of the stack. So before summarizing the stack, let us first understand how the stack will grow. See, as the number of function calls increases, we call it the depth of the calls actually. So in case of the recursion, this is called the depth of the recursion. So if you see, the stack size will keep on increasing with the number of functions calls which have still not completed. Okay, so what happens is the size of the stack will continue to grow. On most of the modern computer architecture, the stack physically grows downwards. Why downwards? Because in the upper areas, some other data structures are stored. So it is basically moving from the high memory addresses to the lower memory addresses, because lower memory addresses are reserved for some system related data structures. So generally the stack is allowed to move only from in the downward direction. So there are some other hardware trackers. So you have the stack pointer, and then you have the base frame, base pointer, or what we call as the frame pointer. So it stays fixed at the base of the current function's frame. So local variables can be found. So generally, so that is how the stack works. So now, so if I summarize the purpose of the stack, so stack, what the stack does, actually, stack is responsible for managing the function calls, saving the variables, and all other aspects, and ensuring that yes, your program executes efficiently. Now, there is a problem what we call as the stack overflow problem. Means if you have too many function calls without getting completed the earlier function calls, then the size of the stack will keep on increasing. That is called a stack overflow, because you really cannot increase the size of the stack infinitely. So we need to ensure that the stack is restricted, or the size of the stack is limited to what the memory can accommodate. Okay. Particularly with the recursive calls, that's very, very important that we ensure that the recursion ends at some point of time, because there is always a possibility with recursive call, recursive functions, that we have not taken sufficient care and the terminal condition is not arising, and so the program has now entered into an infinite recursion and program is not coming out. So that causes a stack overflow error, and that's a very serious error. And it may result finally into what we call as the stack heap collision, and that's what the talk, another part of this talk is. So but it has some limitations also. So the white stack is excellent for handling the predictable structured flow of function calls and local variables. It has rigid limitations because of its size, because it cannot grow infinitely. It is allowed to grow only up to a limited size. And more importantly, whatever data, the local variables, they are destroyed the moment a function ends. So that is another difficulty with stack. Now, if you want to preserve some of the variables which are used within the functions, particularly the static variables, then we require the stack. They cannot be saved onto the stack because that is a limitation of the stack. And the another aspect is, if we are using for everything to be used, we need to use the size at the compile time. So variable sizes and all those memory requirements need to be computed at the compile time. Then and only then we can use the stack. Now, to overcome this limitation, we have another structure called the heap. So heap exists to solve the limitations of the stack, as I've already discussed. So it's a very large unstructured pool of the memory, and it is managed dynamically. So when you have the dynamic memory allocations, they are all managed by the heap. So you can consider it this way, that if the stack is a neat stack of plates, the heap is a giant warehouse where you can rent out the storage lockers of any size. So that's how. This is a very, very important point actually, and this is a very, very important care which you need to take actually, and we call it the heap stack collision. Now, generally what happens is heap, just remember, we have discussed that stack grows from higher memory addresses towards the lower memory addresses, where heap grows in the opposite direction, because it always starts at the lower memory addresses and it builds, or it grows towards the higher memory addresses. There is, if the stack is allowed to grow infinitely, then it may collide with the heap, because it may enter into the area reserved for heap, and that's a very, very dangerous situation. And if a program undergoes heavy execution demands, both segments will expand and that is shown here, that this will collide. So stack is one case, and another one is the heap, and both of them will collide here, and your program counter is now, your program execution stops. It's a very stops actually. So it's a very serious system exception, and your program will terminate here. This is some detailed execution. Okay, so this is how the stack grows is shown here. So your initial process is on the leftmost side. So initial process, you have a stack, you have heap, you have the data, and then you have the system frames. Okay, now you keep on calling the function, so stack keeps on growing. Now stack is growing. And so you have pushed the arguments, you have the return address and all those things here. Now you have another function called function 2, then you have another function 3. So that's how the RAM layout becomes actually. Okay, and then this is the heap here. Okay, that's how the stack grows, and it may cause a very serious situation of collision. So we need to take care of it. With that, actually, I end this talk. So what we have discussed here is the program life cycle, the execution process, and the purpose of the stack during execution. We have discussed. Also discussed the various data structures used during the compilation process. A little bit of the purpose of heap, though the heap serves a lot many other purposes also, but just keeping this lecture, for the purpose of keeping this lecture simple, I have not considered detailed aspects of the heap, and then we have also considered the heap stack collision. So with that, I end this particular talk, and I hope you find it useful. Any questions can be posed to me on my official mail ID, and I'll be happy to answer those questions. Thank you very much.